Okay, this flip lecture is on uniform circular motion. And of course, non-uniform circular motion is coming. Uniform circular motion means you go round and round and round and round without speeding up. Okay, or slowing down, of course. So you go round and round steadily. The first thing we need to do, as always, maybe to get quantitative, is set up a coordinate system. And just for the moment here, I'm going to set up a coordinate system so that theta is measured from the positive x-axis. And this will be r, the radius, to the particle that's going round and round. We have a radius and we have an angle. And from that, it's easy to get the x position. So uniform circular motion is when theta is steadily increasing or steadily decreasing. So in other words, the theta is equal to some constant times time plus whatever it was at t equals 0. Omega can be positive, in which case this theta is increasing with time, and omega could be negative, in which case this theta is spinning that way with time. And if omega is large, this thing is spinning fast, and if omega is small, this thing's spinning slow. Now the next thing we have to deal with is what units are we going to measure theta in? The normal thing to do is to measure theta from 0 to 360 degrees. In physics, we often do something else, and I'm going to explain why we do something else. The circumference of a circle of radius r, capital C, is 2 pi r. So, if I said that instead of measuring theta going from 0 to 360 degrees, if I said theta can be something in the range of 0 to 2 pi, then as theta goes from 0 to 2 pi, so one revolution is going to correspond to 2 pi. As theta goes from 0 to 2 pi, I trace out the entire circle. And if, say, theta has only gone, say, a quarter of the way around, well, a quarter of 2 pi is pi over 2. If theta has only gone a quarter of the way around, that would be to here. Then how much have we traced out? Well, we've traced out 1/4 of the circumference. So that would be 2 pi r over 4. In other words, that's pi over 2 times r. Just one more example. Let's say you've got 1/3 of the way around. Well, 1/3 of the way around would be 2 pi over 3, and that takes you to about here. Okay, so 1/3 of the way around is 1/3 of 2 pi, which is 2 pi over 3. But that's 1/3 of the circumference. How much that's been traced out? So that's 2 pi r over 3. And if it isn't obvious, what you might have been noticing here, I'll just say it, that however, if you measure angles ranging from 0 to 2 pi, all you have to do is take the angle and multiply that by r, and you get how much circumference has been traced out. That is the trick. If we measure theta in, and we call these units radians, and one revolution corresponds to 2 pi radians, then the amount of arc length traced out, which we could call S, is just theta times r. And if you put in theta equals 2 pi, you get the whole circumference. Here's some other goodies from 4.4. If something's going around steadily with radius r, there's some things we can say. For example, you might start here, go all the way around once, click your stopwatch, go all the way around again, click your stopwatch, go all the way around again. By definition, if it's going around steadily, each of those lap times was the same. Those lap times we call the period, and we usually label it capital T. T is the period. Another extremely common thing to talk about is 1 over the period. So if t was, say, 3 seconds, then it's common to say that the frequency f is 1 over t, 1 over the period. And if t were 3 seconds, in that case, we would have 1 over 3 seconds. So the frequency, the period is measured usually in seconds. The frequency is usually measured in per seconds. And a tiny frequency corresponds to a huge t. And if I put a tiny t, a tiny period in the denominator, I get a huge frequency. So things that have a very short period have a very high frequency. If we use these units, we know that theta is increasing by 2 pi every time t changes by 1 period. So for uniform circular motion, theta of t is some constant, which I'm going to call omega, times t plus the initial, whatever it was, at t equals 0. And over here, we've already introduced capital T, the period, and f, the frequency, which is 1 over the period. So there's actually a relationship here between f and omega. If theta at t plus capital T, well, I can just plug that in here. That's omega times t plus capital T plus theta naught. Okay, so that's equal to the omega t plus theta naught is back equal to theta at t, and then I have plus omega t. So if theta is supposed to have increased by 2 pi as I go from theta at t to theta at t plus capital T, it must be the case that omega capital T is 2 pi. So now we have a formula for omega. Omega is equal to, dividing through by the period, it's equal to 2 pi over capital T. Or, since we've already defined 1 over t to be the frequency f, I now have omega is equal to 2 pi f. I'm just going to derive one more formula which follows real easily from all these ones that we already have. We have theta of t is omega t plus theta of naught. Therefore, theta at t plus delta t is equal to omega times t plus delta t plus theta naught. All I've done is plug in t plus delta t where I had t. Now distribute that omega t, and I've got omega t plus theta naught plus omega delta t. I distributed and I rearranged a little bit. But this is equal to, this reason I rearranged is so that that would be theta of t. So now we have theta at t plus delta t minus theta at t is equal to omega delta t. This thing on the left is worth calling delta theta. That's the change in theta. Divide through by delta t, and I've now got the change in theta over the change in t is equal to omega. Now, eventually we'll get a little more sophisticated than that, because the way I derived this, I derived it for uniform circular motion. I think it would be good if you, at this point, compared this with Knight equations 4.24 and 4.25, so that you understand where this is going when we eventually get to the idea of non-uniform circular motion. That is circular motion that involves speeding up or slowing down. So we're in a good spot to move on to 4.5, which is on what's called centripetal acceleration.